Hey students, I hope you're all well today. I'm doing well over here, although I wish I were with you to have this lecture with you live. All right, we're starting our new unit now about space. It's very exciting, the stuff we're going to be getting into, learning about planets and space travel and all that kind of stuff. Today we're going to start with stars. So, what is a star? Here's the working definition we have. Stars are huge masses of luminous plasma. Which brings up, of course, the question, what in the world is plasma? Well, you know about solids, liquids, and gases, right? Well, it turns out plasma is a fourth state of matter. We used to always say it's the stuff of stars, you know, this kind of thing. Well, it turns out that that plasma, you've seen it. If you've seen lightning, then you've seen plasma. All right, so we're going to watch a little video that gives us a little idea about it. It's going to show a star, but it's going to talk more than just stars. It's talking about plasma in general. Here we go.
Have you ever seen static electricity cause a spark of light? What is that spark? What about lightning, the northern lights, or the tail of a comet? All of those things and many others, in fact 99.9% of the universe, are made of plasma. Plasma is a state of matter, drastically different from the more familiar forms. Take ice, for example. Ice, a solid, melts to become water, a liquid, which, when heated, vaporizes into steam, a gas. Continued heating of the steam at a high enough temperature causes the water molecules in it to separate into freely roaming hydrogen and oxygen atoms. With a little more heat, the ionization process occurs, and the negatively charged electrons escape the atoms, leaving behind positively charged ions. This mixture of freely roaming negative and positive charges is plasma, and at a high enough temperature, any gas can be made into one. These freely moving charged particles behave very differently from the particles in other types of matter. When a doorknob, a solid, has static electricity on it, it doesn't look or behave any differently. And with the exception of a compass or other magnetic object, we rarely see matter respond to a magnetic field. But put a plasma in an electric field or magnetic field, and you'll get a very different reaction. Because plasmas are charged, electric fields accelerate them, and magnetic fields steer them in circular orbits. And when the particles within a plasma collide, or are accelerated by electricity or magnetism, light is generated, which is what we see when we look at plasmas like the aurora borealis. Plasmas aren't just beautiful celestial phenomena, though. Imagine a tiny cube made of normal gas with a very high voltage across it. The resulting electric field pushes some of the electrons off the atoms and accelerates them to high speeds, causing the ionization of other atoms. Embedded impurities in the tiny cube of gas cause it to gain and release a precise amount of energy in the form of ultraviolet radiation. Attached to each tiny cube, a fluorescent material glows with a specific color when ultraviolet light at just the right intensity reaches it. Now, make a rectangle out of 1,000,000 of these tiny cubes, each separately controlled by sophisticated electronics. You may be looking at one now. This is called a plasma TV. Plasmas also have implications for healthcare. Plasma chemists create highly specific plasmas that can destroy or alter targeted chemicals, thereby killing pathogenic organisms on food or hospital surfaces. Plasmas are all around us, in forms that are both spectacular and practical. And in the future, plasma could be used to permanently rid landfills of their waste, efficiently remove toxins from our air and water, and provide us with a potentially unlimited supply of renewable, clean energy.
How about that? More than just the stuff of stars, huh? Okay, so back to our stars now, the definition. Stars are probably going through a process called nuclear fusion. When I say probably, it's because we know science is never 100%, right? We're making a really good guess based on really solid data. So why do we think, and what is this nuclear fusion? So this process is the action of hydrogen atoms fusing together to form helium. So hydrogen atoms have 1 proton each, and helium atoms have 2 protons. So if I take a hydrogen and I squeeze them together, I can make a helium out of that. Now this is something that we cannot reproduce on the Earth. We haven't been able to do this, to make helium. Helium is an element, you can't make it. It can be generated through some processes like radioactivity, things like that, but it's not easy to do. So if this is happening, when that happens, a vast amount of energy is created and released, producing heat and light, which of course is what we see in a star, right? Just like our sun. And so that heat and light can be used for, obviously, for us to sustain life on our planet. Their massive bodies are held together by gravity. Everything that has mass has gravity, and these are massive. And so they're being held together in a sphere like that because of gravitational pull. Furthermore, the gravity of the sun is keeping the Earth going around it in orbit, which we'll cover that when we start looking at the planets. So the characteristics, not all stars are the same. They vary in brightness, color, size, activity. We can see all different kinds of stars. If you look really closely, this picture has been enhanced a little bit, but you can see out there we have yellow stars and orange stars, or actually red, blue stars and white stars. So each one of those, you can also tell some are small and some are big. Then again, we could have a really big one, but it's farther away, so it doesn't look as big, this kind of thing. But there's all different kinds out there. They're really quite fascinating. The magnitude is the measure of the brightness. All right, so some stars are very bright and some aren't. Now, depending on where we are on the Earth, okay, some things will seem brighter to us than other things. We call that the apparent magnitude. That's how bright it is as it appears to us. But there's something called the absolute magnitude. If, for instance, we were able to travel to the actual star, then we would be able to see its brightness better. So say it's really, really far away, it's not going to seem very bright to us. The apparent magnitude is not going to be great, but the absolute magnitude might be actually very, very bright. So if we see here, we're looking at the apparent brightness of objects in the magnitude system. So from our perspective, from the Earth, we can see that you have very bright over here. So our sun is in the very bright category. That would make total sense, right? It's the brightest thing in the sky. It's over here. Then comes our moon. Like on a full moon night, you've noticed how that can be very bright. Venus, known as the morning star, it's usually when you're, the starlight, star bright, the first star I see tonight, I wish I may, I wish I might, have the wish I wish tonight. That's usually Venus that we're seeing, not a star at all, but a planet. We will learn that planets, of course, are just reflecting light. We have a big star here called Sirius right here. Here we have the faintest naked eye star. So only one we can really see with our eye is about at this magnitude here, this apparent magnitude. We have some fainter objects here, which we've been able to pick up with some of the fancy telescopes that have been invented out there. So what about their size, color, and temperature? We have actually rated them, and we put them into this this grouping right here. So mostly we talk about the main sequence, all right? So the main sequence right here are your basic stars. They come in all different colors and sizes. And then we have the weird ones. The weird ones that are outside the main sequence, like the red supergiants, the red giants, the blue giants, the white dwarfs. They're kind of outside the main sequence. This main sequence are producing their magnitude. Over here we're talking about luminosity in sort of predictable ways. Our sun is one of the main sequence stars. It's down here somewhere. It's an orange to reddish to yellow star. We'll get to it. In fact, I think we'll spend a whole week on our sun, which is our star, and how it creates the seasons and things like that. So we'll spend more time on that then. Okay, so if we were looking at our sun, it's right here. All right, so it's compared to the other ones, not going to be that big. Okay, so this would be a giant star compared to our sun. We take that giant star right down and put it all the way down here. So this is that giant one, and these are the supergiants. I mean, they are massive. If our sun were this size, there would be no Earth, all right, because it would completely swallow it, because it would, first of all, be very hot, but it would literally be bigger than the orbital area of the Earth. Here are some of those supergiants right here. This one's called Betelgeuse. We'll see this again. Betelgeuse is a star in one of the constellations we'll be looking at in a minute here. And then we have Antares here, a big one as well. Notice we have ones here, Rigel and Aldebaran, and these coming down here, that's our sun right there, that tiny one. The only reason it's bigger to us is because it's that much closer to us. So how do we know how far away stars are? Because they're so far, right? They're very, very far, and it's fortunate. If they were much closer to us, we couldn't survive. We'd have too much competition with the gravitational pull and the heat and that kind of thing. So we're able to measure star distance through a process called parallax. Parallax is sort of a mathematical trick that we use to figure this out. The closest star to the Earth is obviously our sun. The next closest star is called Proxima Centauri, and we have calculated it to be 4.3 light years away. Okay, so light travels really fast, and so it'll travel a certain amount of distance in 1 year, a way long distance. So 4.3 light years away is a way long distance away. Scientists use this formula to calculate how far away they are, the parallax formula. A star closer to the Earth will appear to move faster than one that's far away. So we actually track its movement, and we have to look at it during one time of the year and then another time of the year, and then that gives us this formula we can use. The change in position of one star in relation to the other star is known as parallax. I'm going to show you a little picture right here. So if we're looking at this particular star, okay, and here we are in the Earth, and from our view it looks like it's right there in January. And as we travel around 6 months later, our view in July, and then we put it through the calculations, and it gives us an idea of how far away it is, and we can count the light years right there. It's a mathematical formula, and we're not going to have to do that math for this class. Hooray, right. Right, we're science class, not math class. What is a variable star? So it turns out that some stars don't have a constant magnitude. So in other words, they'll be bright one day and not so bright another day. And so for the longest time, scientists wondered what in the world is going on with those stars. We see stars acting strangely. Even back in the old days, before they even had telescopes, man would look up into the sky and he would notice differences, and they would make some sort of conclusions. They would draw conclusions about that. Some of them scientific conclusions. Sometimes it would be religious, like they were wondering if the gods were angry, things like this. Some will change in brightness regularly or repeatedly. Those are called variable. We're going to see what kind of causes that. The pulsating variable star goes through periods of swelling and brightening, then shrinking and dimming. Okay, so that's one way of doing it, through the pulsating. Another way is called eclipsing variable stars. They appear to change in brightness, not because they're shrinking or dimming, but because one star is orbiting another star. And when one comes in front of it, it actually will change its apparent magnitude from what we can see. Here's what it looks like. So this is our eclipsing binary system right here. So I have two stars, and they have a certain brightness. So you're going to see that certain brightness is about this level right here. Well, when this happens, when this little red star comes in front of the yellow star, it's called a primary eclipse, and our brightness changes, okay? It gets less bright over here because this is kind of dimming it a little bit. Then they go back to our baseline, and then it gets, eclipsed the other way, and it's a secondary eclipse right here, and that brightness is changed again a little bit because some of that orange we can't see now. And then it goes back to its baseline, and then once again primary. So what we're seeing from here is bright, not so bright, bright, not quite as bright, bright, and not so bright. So for a long time it took us so long to figure out what in the world was going on. And so by watching closely with other really fine telescopes and space telescopes, this is the working theory we're using on the eclipsing binary stars now. It seems to work. And it seems to be very good evidence to show that this is indeed what's happening. So what's a supernova? Sometimes we see a star that wasn't visible before. Okay, so there's a blank spot. This was really a famous one. The ancient Chinese saw a star that appeared in the night sky that hadn't been there before, and they thought, wow, That's crazy. Where'd that come from? And then this new star would then fade over the next few weeks or months. And that's pretty quick when we're talking about, stars, right? Weeks and months. So we believe what happens there, and this is actually from the work done by the Chinese. The Chinese kept great records. We're talking about ancient Chinese. They kept great records, and much later we looked up in that part of the sky where they had said this giant star, got big, and we found behind it something very fascinating looking. We believe what happened was that there was a star that went through the death throes. It suddenly flares up, becomes much brighter than normal, and it explodes, and it spews this what we call stardust and gases into space, leaving behind the remnants of the star called a nebula. Nebulae is the plural of it, and this is what it looks like, something like this. I'm not sure if this is the Crab Nebula, but if it is, that's the one the Chinese saw, and it disappeared. So this thing they could not see anymore from the Earth. But now when we put our powerful telescopes up there, we do see this dust cloud. I will say also the dust has been helped to be colored by a computer, which has helped it to be more visible this way. All right, so but we trained our telescope up in that area and found this, and we believe that was the death of the star known as a supernova. Neutron stars are fascinating. Scientists believe that some supergiants will collapse, and then of course it forms a high pressure at the core and it crushes protons and electrons together to make neutrons. Now we know from radioactivity that protons and electrons together probably are what form neutrons, with something called a little neutrino that's in there. But remember, this is very much still theory. We haven't been to these stars, obviously, and this is just a working theory like all science. It seems to have some fairly decent evidence behind it. So it becomes a tightly packed, with this theory, a tightly packed neutron star. Very dense. It would weigh a lot, so a teaspoonful could weigh 1 billion tons, according to this theory. So that's interesting. That would be our neutron star. Then we have a pulsar, which is a neutron star. That says stat, but it's supposed to say star, that spins rapidly on its axis, flinging out these pulses of energy into space, flinging out some of that plasma into space. This is a picture. This is an artist's rendition of what that pulsar might look like. It's flinging that plasma out like that. Okay, so very, very densely packed. Probably used to be a giant, supergiant. Which brings us to black holes. Once again, only theory. Okay, so this is a theory that states that sometimes when a supergiant runs out of its fuel, because they're burning, that hydrogen and helium business, the gravitational force will cause a great collapse. It'll all pull inward, okay, because gravity is such a powerful force, pulling everything nearby with it, including light. It sucks it all in there. This is known as a black hole because not even light can escape, and we can't see it anymore. Once again, I have an artist rendition of this here. It looks like a giant, flushing toilet or something, right? All being taken down into this black hole. Remember, this is just a theory. We don't know for sure if this is what's going on. Some people believe that the center of our universe is a black hole and what we're all spinning around. We are definitely spinning around. All of our galaxies are spinning around like this, and eventually could end up in this black hole. Eventually, being millions and millions of years. So no worries there. It might be fun to do a little research on black holes and what they've come up with more recently. Now, constellations are just looking at, when we look up at the sky at night and we see all the stars up there. Sometimes, you know how sometimes you go on a summer day and look at the clouds and it looks like they're forming, creatures or patterns or something. Well, so that's what the ancient peoples would look up in the sky, and they looked and they found patterns in the stars. Now, these patterns are just the way they look to us from the Earth. Okay, so they're imagined pictures. We have 88 official constellations based on what's known as the zodiac. The zodiac would be the gods and things of the ancient Romans and Greeks. The Chinese were also looking up in there and finding some interesting constellations too. So because we're spinning and because we're going around the sun, we see different constellations in different parts of the sky at different times of the year. So you may not have thought about that, but it does change based on the season. So when we look at it, so their stars are all in different locations, okay, with different magnitudes, different apparent magnitudes, different distances, all that kind of thing. But from our eye, it looks like this, okay? They're not all in that pattern in space, but to our eye on the Earth, they look at it. They look like that. This happens to be a constellation known as Ursa Major. It's just part of it, really. I'll show more of it to you here in a minute. Do you recognize that? Here are the other ones. So the equator here, right? And we can see that there are different names of constellations up here. So let's see where we are supposed to be. Some of these you might recognize. For instance, right here we have the constellation Orion, which is very evident in our sky all year round. And then, where is it? Ursa Major, right up here. Okay, so we see Ursa Major. We were just looking at part of it, this part right here. Do you recognize it? It's what we call the Big Dipper, right? Leo Minor, all these different ones. There's one called Cassiopeia that looks like a giant W. Are y'all seeing it? I don't quite see it on there. Anyway, also, we live in the northern hemisphere, we're going to see certain constellations that they will never see in the southern hemisphere. I believe Ursa Major being one of them. So the Big Dipper is only visible in the northern hemisphere. Whereas they have ones down south we've never seen. For instance, the Southern Cross is down there. We've never seen it. So this is Ursa Major. So it stands for, Major is going to be the big bear. Ursa is a bear. And so we see this part of it and see the Big Dipper, right? And it turns out all the rest of this is part of that constellation as well. And it's supposed to look like a giant bear. What do you think? This is how they were thinking of it in the old days. Now, I think it's kind of weird that this bear has a tail. Yeah, I don't know about that. But this is the Big Dipper part of it right here, if we put a little line right there, like that. So I don't know if you'll agree with the people who called it the Big Bear. But what you find interesting is, now these words here are in Russian or something, I'm not exactly sure. But at different times of the year, the Big Dipper is either, open or emptying, right? Emptying out right here. But one thing you can count on is if you trace these stars right here and you go from this one to this one and keep going, it's going to end you at the North Star every time. So they're rotating around the North Star. See, I'm going to end up at the North Star. I'm going to end up the North Star and here at the North Star. So if you're sitting out one night and you see the Big Dipper, it catches your eye, follow those last two on the cup right there, and you should be able to find that North Star that tends to stay right there in the north, so it's only seen in the northern hemisphere. It does wobble a little bit, it kind of goes around a little circle like that, but it stays in essentially the same place in the sky. So pretty cool. This is Orion. Okay, so Orion is the great hunter. To be honest with you, I'm not sure of his story in ancient literature, Greek literature, Roman literature. I'm not sure about it. But what I do know is that his constellation is visible from our part of the world all year round. It does change place in the sky. Right now it's moving, I think, towards the eastern sky, and in the summertime it'll be in the eastern sky. So let's see, this is what it looks like. And then supposedly this is the hunter right there. So we can see Betelgeuse. Remember we saw that's a massive, massive star, right? And then we can see these other ones, and here's Rigel, another very bright star right here. So how does that look like a hunter? It looks like his arm is holding something. I'm going to show you an idea here. This is someone's idea that you see we have Betelgeuse there, and let's go back again. So he's supposedly holding a sword of some sort. Oops. And then holding a shield. Let's see. You see it? I've seen other ones that have him holding a dead lion. So one thing that's very noticeable, though, is his belt and his scabbard, where his sword came from. Let's go back again. See, there's the belt of Orion. Orion's belt. Here's the scabbard hanging down, his scabbard holding his sword. All right. So check out the sky and see if you see it. It's visible right now. One of the great ways to look at stars, of course, is through a telescope. If you have a telescope, this is a great time to pull it out, take a look at it. It might frustrate you a little bit because, the Earth is spinning, and honestly, it's spinning pretty quickly, pretty fast. So you may put that telescope on a star, and you'll say, oh, there it is. Come look. Mom, come look in here. And she'll look, and I don't see a star because we've moved that much already in that amount of time. When you're looking at using this kind of telescope, this is called a refracting telescope. You look through here and you look straight at it. It's almost like a pirate's telescope. You point it at the star and you see it. You have a lens that is going to concentrate the light, bend it, and then put it through another lens for your eye right here, and you're looking straight at it. These were the original telescopes that were made back in the day, back in the 1500s or so. You know, Galileo took one and made it better, but this is a better telescope. This is called a reflecting telescope. You're actually looking in the side right here. You're pointing to the star this way. There's a mirror down here. All right, so the light comes in here, here's the mirror, and it bounces off another mirror and you see it. So I know that Isaac Newton really preferred using a reflecting telescope because he believed that it actually got a sharper image on the mirrors, and that's true. Of course, it depends on the quality of your mirrors. If they're the bigger they are and the smoother they are, the better they're going to be right there. But they do tend to make the best telescopes. This is the greatest telescope ever. This is the Hubble Space Telescope. So when we are down here on the Earth looking through a telescope, we have the lenses in there which help to refract the light, right? But furthermore, we have to look through our atmosphere. And the atmosphere is a lens of its own. So it kind of changes the way things look. In fact, it's really the atmosphere that causes the stars to look like they're twinkling. All right, so that's why the twinkling of the stars is really from our atmosphere. Okay, so this telescope was designed by some incredibly brilliant men, named after a man named Edwin Hubble, who did a lot of exploration in space. He was a great astronomer. Not to be confused with astrologer, which is studying like the magic of the stars or whatever. So we have, this is out in space. So then we get away from the atmospheric interference with the way the stars look. And we've seen some amazing things deep, deep into space. For instance, this is a nebula. So remember we talked about a nebula, probably exploded star. It is called the Horsehead Nebula. Do you see a horse head here, really? I don't know, maybe. This has been enhanced by a computer, so we can see it a little better there, but we'd never had seen it before. Maybe this is the horse head, huh? That kind of looks like a horse head. But it is known as the Horsehead Nebula. Here's another incredible nebula that's been seen from the Hubble. The Hubble is up there. It's interesting, when they first sent it up, they had done the calculations for the mirror on it and had made a slight mistake. And so when they sent it up and the first images they got back from it, they were all blurry. And everybody was so disappointed. It had to do with the parabola of the mirror that was in there. Was slightly off. And so they did more calculations. They decided what was wrong. They made a new mirror. And then they took, the space shuttle actually took the new mirror up there, and some astronauts replaced the old mirror with a new one. And I'm talking about a big mirror here. And that's when we started to get these just incredible photographs from the Hubble, which we're still getting. Here's another one. I'm not sure what this one's called. It looks like someone's piece of art there, doesn't it? That's crazy looking. And these are deep, deep out into space. We're going to take a look at a video here. Let's see what this is about. right, so y'all get the idea. Those are some of the images we've captured from the Hubble Space Telescope. Okay, so stars tend to collect up in groups. They're held together by gravity, the smallest group being those binary systems like I showed you earlier. Multiple star groups can have up to 100 stars. Then there's star clusters, which have several hundred up to 1,000,000. And then we have galaxies. So in that video you saw that there were a bunch of galaxies in there. So those galaxies are made up of millions and millions of stars each. Okay, so we're going to look at some of those. So here we're just looking up at just bunches and bunches of, millions and millions of stars, right? So our binary system, which we saw earlier, just 2 stars. More than half of all star groups are binary. Interesting. We have one called the Beta Lyrae, okay, and then they can go through that the eclipsing thing, so the variable magnitude thing going on there. Okay, so here's just an artist's rendition of maybe stars who are rotating around each other, a binary system. Star groups right here, we're going to be seeing different ones, Castor, Antares. We have our sun over there, that kind of thing. Okay, see different sizes, different colors. And then we have our clusters, like for instance the Pleiades right over here, which we could also say as a constellation, right? No particular arrangement, they just happen to be there together. The Pleiades are, a group of ladies from ancient Greece or whatever. Every now and then in August you'll see from this particular direction, not from these stars, but from that direction, we have a meteor shower that comes in, and we call it the Pleiades because it comes from that area of this star cluster. Several hundred to a few thousand stars in here. When you put the telescope on there, you can see all sorts of amazing stuff. Globular star clusters, we saw some of that in the video as well, contain several thousand to 1,000,000 stars. They tend to form in the shape of a ball. They get close together. They look kind of like a big fuzzy ball to us from the Earth, something like that. That's probably a pretty good view, actually. And then we get to galaxies, can contain millions and billions of stars. They stretch over huge areas. We are in a galaxy. Ours is called the Milky Way. I'll show you a picture at the end that explains why it's known as the Milky Way. It is called a spiral galaxy. The best we can tell, it's a spiral galaxy. There are other shapes called the barred spiral. Sometimes people think that the Milky Way might be a barred spiral, but it's one of those two we think, and it has to do because the plane that it's on, it's sort of flattened out rather than globular. There's an irregular shape that doesn't have any particular shape, and one called elliptical. We can put galaxies together depending on where they are, and we call that the local group. So here we see some elliptical right here and some spirals. So we're supposedly one of these. We're looking at it face down. If you turn it on its side, it would look kind of like a plate. And then our barred spiral. Some people think the Milky Way is a barred spiral. We don't know for sure. There's what a spiral looks like. See, so it looks like a flat plate and all those stars spinning around there like that. Some people think that maybe in the middle there might be a black hole. Don't know. Maybe in the middle of all the group of galaxies there may be a black hole. So you can see here, this I believe is the Milky Way galaxy. Is that right? Yeah, because the sun location right here, so that must be us. It looks a little bit like a barred, this is somebody's drawing, I think, right here. And you can see that there's the arm of Sagittarius. That would be one of the, constellations that we're seeing, right? So those are spinning around too. And then we're in the spin too. We're in that big swirl right there. We see some globular clusters out here, a dwarf galaxy out this way. We're getting more and more information as we do more and more research with those fancy telescopes. So here you can see the Milky Way. So the idea here, on a really dark night, if you're out in the country, not too close to the city of Austin, because it has, even all night long, has a lot of light. We call it light pollution. And it washes out the stars. Furthermore, if there's a full moon, it washes out the stars. So you'll notice on a new moon, when it's really, really dark, if you're far away from the city, you will see lots more stars in the sky. You might, where you are, because we kind of live out in the country, right, have more stars in the sky. I'm kind of close to Austin. Not that close, but I still see the shining lights of Austin, up in the sky every night. But if you were out you could see something like this, and that's why they called it the Milky Way. It looks like someone spilled a glass of milk across our sky, showing all of those other stars that are in our galaxy with us. We're all spinning around together, including the constellations we see. Here's a really good picture of that spilled milk across the sky. Beautiful. Okay, so that brings us to our lab time. And so what we're going to do is that I will send you along with this link, or maybe in a separate email because I don't want it to get mixed up with the link. You're going to get a video link for this, obviously. But I'm going to send you some pages of constellations, and you can have those printed out. They look different from the one you're seeing on the page right here. Those are just pages of constellations. And what I would have you do in class was you'd pick one, and then I have those little foil star stickers. And you could put those on there. Remember, they're different colors, so we could, figure out what color the star is and put it on there and match those up. You can just look at them. You don't have to print them out and do that if you don't want to. This other activity right here is this viewing projecting tube. So I'll send these to you as well. They look like this, and you can pick one of them. And what you'll do is print those out, cut out the circle, and then put it over a tube that you make from, you can use a toilet paper roll or a, paper towel roll or something like that. I just use cardstock, and then make it the right size, and then you tape that, so you cut this part out and put the tube, this part around the tube. Sometimes you cut little cut little cuts in the side here so it will go around the tube. So now this is over the tube, and you take a toothpick and you poke through those holes. All right, so now you can take and look up with your eye at light, and it will look like what the constellation looks like. You could turn it around backwards and shine a light through it, poke those holes in, shine a light, and project it up onto your ceiling. Something like that. So check that out. See if it works. It would have been nice to be able to work with a telescope today, but of course we have class time during the day, and we can't look at the sun, so that wouldn't work very well. So just, if you have one, go ahead and take a look at some stars tonight if it's a clear night, and have fun with that. Okay, so next time we get together, we'll talk about other things in the sky, like asteroids and things like that. So it'll be a lot of fun. Okay, thanks, y'all. Have a great week. See you soon.